I will, yeah. So what we are trying to do in these waveguides is we want to confine the electromagnetic energy in two dimensions and let it propagate in the third. So think of these waveguides as basically pipes for waves. We want to be able to guide this electromagnetic wave in the direction we want it to go. We want to be able to modify things in the direction we want to go. You may be very familiar, or at least I'm sure every one of you has heard of a waveguide which is used throughout the world today, and that is, as an example, is the optical fiber. But what you may have not realized so far is that the transmission lines you have been working on so far in the course are also waveguides. Let's try to first understand why we need to go into these waveguides. Like, why doesn't the transmission line theory, which you have been working on in your Unit 1 and Unit 2, why isn't that just good enough? Why, why is, why do we need to really do this complex maths, which we'll be doing over the next 3 or 4 weeks? Why can't we just live with the simple maths we created for the transmission lines? So far, what you had been looking at transmission lines, and let's just take coaxial cable as an example. Basically, if I have a conductor surrounded by another conductor, this is one very classical transmission line, which I'm sure all of you have already worked with a coaxial cable or an SMA cable for RF regions. You have a conductor inside and you have a conductor outside. The conductor inside is trying to carry the current in one direction, outside is carrying the current in the opposite direction. But effectively, what you're doing is, and going back to the course you took in the last semester, is that you're creating an electric field which is only present between the two conductors over here, and a magnetic field which is going around these two conductors in a cyclic fashion. This was the work you did in the last term, where you had to calculate the inductance per unit length and the capacitance per unit length, first having calculated the electric field distributions and then having calculated the magnetic field distributions. What you have done in the transmission line is you took this and you represented it by a circuit model of an LC capacitor, taking advantage of all the electrical circuit work which has been done in the last 60, 70 years, or actually more than 100 years. You represented this as a simple L and a C circuit, and you basically said that this transmission line has a characteristic impedance given by Z naught, which was square root of L by C. And then you looked at what happens if I have two different transmission lines of two different Z naughts, and I start to, what kind of reflections do I get? How do I correct for those reflections? How can I match different loads on these transmission lines? And that works very well in the discrete circuit world, or in the low speed, or in the low speeds. And when I say low speeds, I mean few gigahertz. That works pretty well in that case. Let me ask you a question. Let's see if this knowledge is complete. And to see that, let me ask you a question. What do you think would happen if I have a coaxial cable feeding into, let's just say I have a coaxial cable here, and I have on another end a microstrip line, I have a coaxial cable on one end and I have a microstrip line on the other end, and I'm connecting the coaxial cable to a microstrip line. This is a problem you normally always see in your PCB boards. So you have a coaxial cable or a SMA cable coming in, and then on the PCB board you have a microstrip line with a metal on the top and a ground plane on the bottom. What happens if I connect these two together? And let's say that you have designed these lines such that the characteristic impedance of the coaxial cable is 50 ohm, and the microstrip line is exactly the same as 50 ohms. What you have learned so far, you would tell me that this is effectively as if I am going from one line which has Z naught of 50 ohms into another line which has Z naught of 50 ohms, and thus right at this boundary of these two lines there won't be any reflection which would be created. If I look at the reflection gamma at that boundary, gamma would be the load minus that, so it would be basically acting like a matched load, and thus gamma would be zero. Then when I connected this to coaxial cable with a microstrip line, and even though I have managed to maintain the characteristic impedance the same, the circuit model tells me that it doesn't matter how the electromagnetic field is distributed, I would still get no reflections. And then obviously comes the issue, right? Now you can start thinking there's an issue. In the coaxial cable, the electric field is going something like that, and the magnetic field is circulating around. In a microstrip line, the electric field is probably going to have some curvature. The electromagnetic field confinement in this case and the electromagnetic field confinement in this case is actually quite different. And if you do the actual calculations, if you do the calculations from the electromagnetic field, you'll see that even though the characteristic impedances are exactly the same, you would still see some reflections. The reflections would be minimized when you make the characteristic impedance equal to the same, but it won't be zero. There would still be some reflections left. And that would be because the electromagnetic waves are not necessarily, the electromagnetic field confinement is not exactly the same. So I'm going from a, a different field confinement to another different field confinement. They're not going to match with each other. Some of that electromagnetic field is going to be thrown back at me. So the circuit model is a very good model which works very well for most of our applications. But as you go to higher and higher speed, that model starts to break up a bit. And that model doesn't tell you everything which is there, which is going to happen in various structures. In fact, when you go to high speeds and you have to send from one waveguide, from one kind of cable to another cable, you have to design some specific tapers which allow you to match the electromagnetic field from one to the other and achieve minimum reflections. So that transmission line model doesn't tell you the whole physics of what is going to happen. Further, the transmission lines you have looked at so far, most of them, they propagate TEM waves. And we'll talk about what these TEM are. You may have already heard this word in your last semester when you were doing various. You may have already heard about this in last semester when you were doing various uh, 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 plane waves, for example. But the TEM means transverse electromagnetic waves. TEM waves only happen in systems with two conductors. And these are things we'll explain further. We'll go about and we'll add more to these things later on. But TEM waves only happen in systems with two conductors. For a coaxial cable, you in fact do get TEM wave inside. For microstrip, you do not. You do not have a perfect TEM wave. So again, now you start seeing there's certain cables which work well. Sorry. There's certain cables for which that circuit theory works well. That circuit theory which you is developed, that circuit theory which is based on L and C, the effective inductance per unit length and the effective capacitance per unit length, is based on the assumption that there is a TEM wave going through the through the cable or through the transmission line. It's only accurate for those transmission lines where there is a TEM wave. But there are many transmission lines where the TEM wave doesn't even really happen. And not only that, as we will learn later on, as we will look at this TEM wave for one specific waveguide, we will see that the loss of the TEM wave increases quite appreciably as you go to high frequencies. As you go to higher and higher frequencies, the loss which is created in the TEM wave goes becomes very, very large. And thus the power transmission through the electromagnetic through these transmission lines becomes very, very poor. If you take a look at your standard Cat5 coaxial cable which you use at your homes for your cable TV, for example, it can only transmit close to maybe close to 1 gigabits per second over few hundred meters or few tens of meters. That's the maximum it can transmit. If you're going to satellite systems which are working at 2.4, 5.6 gigahertz, these kind of cables become the transmission line cables which we have been looking at before. There's some feedback coming. Is my voice clear to both the lectures? Okay. The this excess loss becomes quite prohibitive. If you're going to the new systems which are being designed at 60 gigahertz, these are the systems which are being designed for either short haul communication. These coaxial cables or any such type of coaxial cables become almost impossible to use because of the loss they have within them. So we need to find ways to confine this. We still want to be able to confine the electromagnetic energy, and we want to be able to send the electromagnetic energy from one place to the other, and we want to be able to make bends as we are going through. So we need to find better ways than just a standard transmission line which you have been studying so far, and figure out, are there any other better ways to be able to do that? And the answer to that is a waveguide. The waveguides we are going to consider today, consider in these lectures, are going to be, we'll start with a very simple case, and that's called a parallel plate waveguide. Basically, two large conductors separated by a distance, almost like a parallel plate capacitor. This is called the parallel plate. We'll see what happens. Let's say if I have two very large conductors, but they are spaced across 2 points, between two spaces. What happens when I send in an electromagnetic field inside? What happens to that electromagnetic field inside? How does that electromagnetic field get guided through the structure, or can I even create some guidance? We'll extend this later on to a rectangular waveguide. The first case is mainly a case of hypotheticals. It's a case of, hey, let's start building the math to see what we can do. The second case is what is used a lot. Basically, what we have is a rectangular structure, a rectangular metal. So this is metal or a conductor, and with some space on, with some dielectric in the middle, and we see how we can confine light or confine electromagnetic wave within the structure. What are the rules for that? What kind of structures we see? And then we'll go and we will start to create a cylindrical waveguide. Still all metal. If time permits, I'll show you how this cylindrical waveguide leads you through an optical fiber. So this is the plan for the next couple of weeks to understand what happens to electromagnetic waves when I try to confine them within some metallic structure. When I try to send this electromagnetic wave within a confined space, within a small space, the space is being bounded by the metallic structure. What happens to this kind of solution? What kind of a solution do I exist? Before we start looking at any questions on the plan? All right. Before we start looking for the solutions, let's review our Maxwell's equations and what we had done in the last semester when you were looking at electromagnetic waves for uh, different for plane wave structures for unbound mediums. You know Maxwell's equations, and almost I always say that any electrical or electronics engineer should know these equations by heart because the whole discipline of electrical engineering came out of these equations. Maxwell's equations start with Gauss law, which is del dot D is equal to rho, which is the Gauss law, and you spend at least one full week on looking just at Gauss law, which basically says that if I have a charge in a space and I create an enclosed surface around that space and I look at the total flux coming out, the total flux coming out would be proportional to the charge inside. Del dot B, D is equal to rho. The second equation is del dot B is equal to 0. And this is something which we know from since we were kids, which in our kiddish, when we were kids, we used to know that if I take a magnet and I break it, I still get a north and a south pole. I can keep on breaking the magnet, I will always get a north and a south pole. In terms of engineering, basically this means that the magnetic field B has to close on itself. The field is like a dog chasing its own tail. It cannot diverge out. The divergence of this field, del dot B is the divergence factor. The divergence of this field is 0. This field has to close on itself. It is like if I take a sink, fill it with water, and I remove the stopper. the water will go around in a circle like in a funnel. This field has to do that too. The next law was the Ampere's law, del cross H is equal to J, and then Maxwell's genius, which was del D by del T, which is your Ampere's law, and this was your displacement current. This was the term which Maxwell introduced, and it was because of this term that these equations are credited to Maxwell. Del cross J, the first part of this term, is again something which, as electrical engineers, we are very familiar with. If I have a current carrying wire, I would create a magnetic field around it. I would create magnetic forces around it. That's how we make electromagnets. Um, I'm sure most of you have taken a nail and a spun wire around it and made passed current and made a magnet out of it. Del D was the term which Maxwell introduced. He said that as the Maxwell's law, as the Ampere's law stood, del cross H is equal to J. That did not work well with the charge continuity equation. Del cross J is equal to J means that there should never be any new, there should not any divergence of current ever created. Del dot J should always be equal to 0. There should never be any divergence of the current, which we know is not true. Anytime we add a source, we create divergence of the current. So he said, in order to back, make Ampere's law jive with, make it compatible with the charge continuity equation, we have to add this term del D by del T. And the last equation is the Faraday's law, which is del cross E is minus del B by del T. This is your Faraday's law. If you take a look at these equations, there are four field terms here, which is B, H, D, and E, and two source terms, which is rho and J. But B and H are not independent of each other. B and H are related by the property, the magnetic property of the material they are in. So B is equal to mu H, and D is a mathematical term which is introduced so that we can account for the polarization within the material. And so D is equal to epsilon E. So in fact, there are four different field terms, but they are in pairs of each other. They are related by the material properties, where again mu is your permeability, and it is basically an indicative of how strong a magnet can I make of that material. And epsilon is your permittivity, and is an indication of how strongly would that material polarize if I apply an electric field to it. How strongly would the charges separate within that material if I apply to it? If I apply some electric field to it. You had then looked at some specific cases. Hello,
Sir,
is there a question or
sir, I don't get you.
was there a question or
Oh, sir,
no? Okay.
didn't get you.
So we had then looked at some specific cases where we had gone to source-free homogeneous mediums by source free. We basically said the sources are not there, that the wave is created somewhere else. So rho is equal to 0 and J is equal to 0. The two source terms, rho being the charge density. I'm not adding any charge into my system and I'm not passing any current through my system. But I really want to understand what happens if I've created an electromagnetic wave somewhere. How would that electromagnetic wave go through my materials? And we had said that force free and homogeneous medium basically mean absolute and mu did not change in space. That the material remained the same everywhere else. These equations had then boiled down to simply as del dot D is 0, del dot B is 0, del cross H is absolute del E by del T, and del cross E is minus mu del H by del T. Just substituting rho is equal to 0 and J is equal to 0, and substituting the fact that D is equal to epsilon E and B is equal to H. We have then further said we are only interested in solutions of a specific harmonic, that whatever electromagnetic wave I'm creating is varying with a frequency omega. And I want to find what the solution is for that frequency omega. So I am only interested in looking for solutions of the form EXYZT, which vary in space EXYZ EJ omega t. Again, we use the phasor terms. And we had said all I'm interested in is whatever wave I'm creating somewhere else, that wave is varying in its amplitude at the source at a specific frequency omega. If it has multiple frequencies, we can obviously take care of that by just adding different terms together. Or if it has some other particular time form, you already know Fourier series and Fourier transforms. I can break them into different omegas and I can still get my answer. So let me figure out what happens to a specific harmonic, to a specific phasor, to the case. In that case, and this becomes the governing equations now, these are the equations we are going to use for the rest of the term, here. So we had an equation which was in H, del cross H is epsilon, sorry, del E by del T. And if I substitute the value of that E is varying in Ej omega t, H should also vary in Ej omega t. I have del cross H uh, XYZ Ej omega t is epsilon. When I do the derivative, I get J omega E XYZ Ej omega t. And these phasor terms will cancel out, and thus I get an equation only in space now, which is del cross XYZ is J omega E XYZ. Similarly, we have the other equation, which is now del cross E, which is varying in space, is related to H as J omega, sorry, there's epsilon E here, J omega mu H XYZ. Further, what we had done, we had said that if I take this term and I do another curl on it, or I take this term and do another curl on it, then because this is in space, this is in time, I would get del cross H. I can interchange the time and the space components, and I'll get del cross H, and I can substitute the other equation. And we had seen that we ended up with two equations, and I'm just giving you this as a revision without doing the derivation again. We had ended up with an equation which was the Helmholtz wave equation, which was del square E x y z omega square mu epsilon E x y z is equal to 0. And similarly, you have an equation in H x y z plus omega square mu epsilon H x y z is equal to 0. And these are your Helmholtz wave equation. What you notice in the Helmholtz wave equation is that this equation here or this equation here is now only a function of h. It's a second order differential equation. The second order differentiation happens in space. The time component, the variation of the electromagnetic field in time, that time component is accounted for in this term omega square. The material properties, the material through which the wave is traveling through, are accounted for mu epsilon, and then the equation here is now just an equation which is only in one specific field. The top equation is an electric field, the bottom equation is a magnetic field. So I can start looking for solutions now. I don't have to interdepend, I just have one second order differential equation, and I can start looking for those solutions. Also remember, one field is chosen. Once one field is solution of one field is found, the other field is not left independent. The other field would depend on the first field. Let's say I use this equation to calculate the electric field in some arbitrary geometry. Then my H field would be dependent upon the H field here would be dependent upon this curl of the electric field which I have calculated. H field would not remain independent. As an example, we had seen the plane wave last time. We had said that our E only varied in Z direction, but it pointed in X. The amplitude was some arbitrary value E. It traveled in Z direction. We had said E minus jkz. But because this is a vector, it pointed in X. As soon as we had said that, the H automatically got determined, and if the electric field was in X direction, H had to be in Y direction, and the H was given by eta E minus jkz and had to be in Y direction. And these were the only two components which were present. The wave, this was your propagation term. This was your amplitude. And the eta term was your wave impedance. And was given by square root of mu by epsilon. These were the kind of solutions we were seeing in the plane wave, and we spent almost a month looking at various such solutions. Effectively, what we were getting, if we were going to draw it, was that if I have direction x here, direction y here, and direction z, I would have an electric field would vary in z, and E minus j k z is nothing but a sinusoid. It would vary in z sinusoidally. It is a vector, so it would be pointing in x direction as a vector. And associated with that E field, there would be the H field, which would be pointing 90 degrees to that. It may or may not be in place depending on whether mu and epsilon are real terms or have imaginary components to it. But I have basically E field here and I have H field here. And then what is happening to this wave is that over time, this whole distribution is moving forward. Over time, this distribution keeps on moving forward. If I was sitting here and taking snapshots, this whole distribution would move forward as a wave. The electric field is not the wave, the magnetic field is not the wave. Both of these are the components of the wave. They are the two arms. My left arm and my right arm are part of me. So you create this electric field and magnetic field. And another thing you noticed was that the direction of propagation of electric field cross the direction of magnetic field was the direction of propagation. These were the terms we were seeing. Let's add to this move now. So let's say we want to start to find solutions for the parallel plate wave time. The geometry is this. I have two conductors which are very large in one plane, such that they're separated by a certain distance, A, and these conductors are extending in my z direction. And I want to see if I send some electromagnetic wave, how would the electric field here would be confined? What would this electric field be inside, or what would be H inside this space? So they are infinite in y direction. Let's call this direction to be y, or let me let's call this direction to be x, this direction to be y, and coming out of the board to be z. I want to see what kind of an electromagnetic wave would be created, and how would it propagate in this direction. I'm still looking for solutions which are propagating in a z direction. Still looking for those very specific solutions which are trying to propagate in z direction. Again, the equations we have to deal with are the Helmholtz equation, which is del square E x y z plus omega square u epsilon E x, y, z is equal to 0, or an equation which is del square h x, y, z plus omega square mu epsilon h x, y, z is equal to 0. These are the two major equations I have to find solutions for. And related to these two equations, once I have, let's say, I look for a solution of the electric field, then my H is determined too. So related to that, I have to also use del cross E is minus j omega mu H, and del cross H is j omega epsilon E. If I have already found the solution for E, then H will have to be calculated from that solution. On the other hand, if I have already found the solution for H, then I have to calculate the solution for E. But now I end up into one problem here, and I need to get out of that problem. The problem is this, that these Helmholtz wave equations were derived only for two conditions, source free, and the other condition, homogeneous mediums. Source free is still true. In the geometry I have, I'm not adding any I'm not adding any charges anywhere. I'm not passing any current anywhere. All I'm saying is somewhere outside this waveguide I have created an electromagnetic wave. I want to understand how that electromagnetic wave propagates through this structure. I'm not adding any source in there. So this condition is still true. I don't need to worry about that. J is still equal to 0. Rho is still equal to 0. But this condition is not true anymore. This condition is not true because in this specific case, the medium is not homogeneous in bidirection. You have a conductor, then you have some dielectric between that, maybe air, maybe some other material, and then you have another conductor, and then you have something on the outside. There is no homogeneity left, no homogeneity in y direction. So if I was going to apply this equation for the general case, I get into trouble because this equation was derived for the case where there is a homogeneous medium. To get out of this problem, we have to use what we learned again in last semester, and that was the boundary condition. Remember again, these two equations are point form. If I go back to the material, this material inside I'm still assuming is homogeneous within that shaded region. It's still homogeneous within that shaded part. So if I find a solution at any arbitrary point, and somehow if I tie the solution at what happens to this boundary, now here I have a boundary between a dielectric and a metal, and a boundary between a dielectric and a metal. If I tie the solution to the boundary conditions we had learned, then I would still get the right answer. So again, let's remind ourselves of the boundary conditions. The first boundary conditions we had learned was if I have a conductor and a dielectric, let's say the dielectric have epsilon, then if I try to look at this tangential components of electric field, the tangential component of the electric field has to be always zero. This tangential component has to be always zero. Otherwise, the charges on the conductor would readjust themselves till they create an induced electric field in the opposite direction and make that go to zero. So this has to be always and always true. That there cannot be any tangential component of the electric field on the conducting surface. And the other condition is that if I have E normal, the normal component of the electric field hitting the conductor, then the E normal was given by would induce a surface charge which would be given by E normal is equal to minus rho s by epsilon. This comes directly out of Gauss law, and you must have done this in your previous course. So this component of the electric field can exist, and what this component of the electric field, the normal component of the electric field will do is it will induce a charge on the conductor, and this component can still exist. These become your electric field boundary conditions on electric conducting boundary. Similarly to that, you have a boundary condition for magnetic field. The boundary condition for the magnetic field is the normal component of the electric field, B1 normal, B2 normal. The normal component has to be equal, or mu, if this is mu1 and this conductor has mu2, mu1 H1 normal is mu2 H2 normal, and H1 tangential minus H2 tangential, the H1 tangential, H2 tangential is going to induce a surface current which is going to go on this conductor. The magnetic field, the tangential components of the magnetic field are going to induce a surface current which is going to be 90 degrees to this magnetic field. I don't know about you, but I always find this boundary condition to be the easiest to use. The tangential component of the electric field will always be zero. Everywhere else, every other boundary condition, I have to worry about any induced charges or induced currents. I have to think hard through that. But the tangential component of the electric field has to be zero, gives me a very, very interesting boundary condition. So for most of the times, we are going to look for using this. We're going to try to look for using this boundary condition. What happens to that case? Now comes up interesting point. So far, you had looked at unbound mediums in your previous course. The medium was homogeneous in all directions. It was unbound. It did not vary. The electric field was constant in the x and y direction. Life was very easy there, and it did not matter which direction your electric field pointed towards. The solution remained the same. Let's see if that is the case, which is going to happen. What kind of solutions, and the technical word for the solutions we'll see later. Tomorrow's class is called a mode. What kind of solutions can exist in parallel plane. Without doing maths, let's try to understand it physically. Without doing maths, what would happen? If I consider this parallel plane waveguide, we had said this was x direction, this was y direction, and the waveguide is coming in and out of the board, propagating in z direction. If I excite my electric field, if I go from my external source, if I try to excite the electric field such that I have a component of the electric field in this direction Ex, again this subscript points to the direction of the field. So if I have a component in the x direction, that component has to be valued, that component value has to be 0 here. This is a conductor. That component value has to be 0 here. Right at these two boundaries, these component values has to be 0. So there is going to be some variation which is going to happen. So that means that this component, which is pointing in x direction, is going to have a variation in y. And obviously we are looking for solutions in z, so it's also going to have a variation in z. That Ex component is going to have a variation in y, obviously, because either that or it's a trivial, there's no solution, everything everywhere it's 0. It's telling me that at the conductor this value, because it is hitting the conductor tangentially at the two places, at the conductor these two values have to be equal to 0. So it should be varying somewhere inside. So there is going to be a variation in y direction in the amplitude. Again, remember, this subscript as we write it is pointing to the direction of the field. The values we are writing in the parameters or the arguments of the function, this is the directions in which amplitude is varying. These are the arguments of the function. How is that function going to vary? What happens to that now? What kind of H components would be related? So I obviously have previously when you looked at the plane wave, you had Ex pointing in x direction, but varying in z, but not varying in y. And then we had seen with respect to that there would be an Hy component. So basically, based on this, what components of H would exist? Similarly, now, if on the other hand, somehow I excite this component, which is pointing in the y direction, remember, for this component, it doesn't need to go to 0 at the boundaries. This component is hitting normally to the boundary, to the two boundaries. So it does not need to go to 0. But it may or may not have variation in y. So if I excite this component can exist in y without any variation in y because it doesn't need to go to 0, or it may vary in y. I do not know that yet. If I excite this, it can exist at the boundary. So already you see there are there seems to be two different solutions. The behavior of this electromagnetic wave seems to be varying, seems to be different if I have Ex, which is going to hit parallel to my metallic waveguide, to the metal, versus if I excite an electric field component, which is going perpendicular to that metallic component, to that metallic boundary. They seem to have a different solution, possibly a different solution. What could these different solutions possibly be? Let's go back to our equations and let's learn few things, few tricks in the generic term before we start looking for the solutions specifically. The two equations we had were again Helmholtz wave equation. Let's say I'm only interested in the electric field. We have said Exyz plus omega square mu epsilon Exyz is equal to 0. I'm still looking for solutions which are propagating in z direction. I'm looking for those. That the z direction is the direction of my propagation. So I'm looking for solutions which are of the form of Exyz are going as E minus some gamma z, where gamma is alpha plus j beta, and if I substitute it, I get Exyz is Exy E minus alpha z E minus j beta z. This is your propagating term, and this is your attenuation term. E minus j beta z tells me how the wave is traveling in y direction, in z direction, and E minus alpha z tells me as the wave is traveling in z direction, how much energy is it losing to the material? Is there any loss within the material? Is there any loss as it is propagating forward? How is that loss being created? So I'm still looking for solutions of a specific form. I'm still looking for solutions which are propagating in the z direction, which are going towards that. And they could now have amplitude variations in x and y direction. If I go back to my Helmholtz wave equation, the del square becomes del square del x square plus del square del y square plus del square del z square e x y e minus gamma z plus omega square mu epsilon e x y e minus gamma z is equal to 0. So I have now a term. If I just do this twice, I just get gamma square out. So I can turn that and then the e minus gamma z can be dropped out. I have to solve this particular Helmholtz wave equation, del square y square of e x y plus omega square mu epsilon plus gamma square e x y So, just a second. Sorry, it just got a. Okay. EXY is equal to 0. And similarly, I have an equation in H which remains the same form. Instead of starting with E, I could have started with H equation. I get these two equations. For next 2 weeks, these become our starting point. Anytime we are looking for a specific solution, whether it is for a parallel plate waveguide, or whether it will be for rectangular waveguide, or whether it will be for circular waveguide, we would be looking for solutions of this form. We basically start from effectively from these particular solutions, particular equations. Also, now we have the other equations, which are your Maxwell's equations, which determine the relationship between E and H. For example, we have del cross E is minus j omega mu H, and it is not very apparent here, but hidden within this equation, there are three equations. Why are there three equations? Because H, E, both could have all three different components of x, y, and z, and all those would be related separately. What is happening in the x component would not be bothered by what is happening on the y component. So each of those become an independent term. So if I was going to write this equation over here, we can expand it out and we can learn some important things. H could have a component in x direction, could have a component in y direction, and a component in z direction. And doing del cross E, let's go back to the interesting simple matrix form. We have del by del x variation, del by del y variation, del by del z variation, Ex component in Ey, component in Ez. In general case, all these three components could exist. So if I was going to write for the x component, I would get minus j omega mu hx, just the x component here. And just looking at the x component, I just multiply these two terms and multiply these two terms and subtract them. So on the other side, I would get del Ez by del y minus del Ey by del z. Similarly, I would get a term which is minus j omega mu hy is del ex by del z minus del Ez by del y. And I would get minus j omega mu hz, which would be del Ey by del x minus del ex by del y. These are important governing equations of how the fields are going to be related to each other. Remember again, for the specific solutions we are looking for, del by del z will always exist. We are looking for solutions which are propagating in the z direction. So del by del y would always, del by del z would always exist. Del by del x, del by del y may depend on the geometry we have. Notice one thing. If you have a longitudinal component, a component in x or y, which varies in the opposite direction. So if I have electric field in y, which varies in x such that this term is positive or negative, but this term exists is not zero. So if I have a component which varies in the other orthogonal direction, then hz would exist. Or if I have ex which varies in y direction, opposite direction, then xz would exist. So it's telling me an important point from this equation. An important concern you get from this equation is if a field component varies in orthogonal direction, then z component of the other field exists. For the z component to exist, for this xz to exist, I should have electric field in the y direction, and not only should I have electric field in the y direction, that electric field should vary in x direction, or I should have electric field in x direction. Again, remember the subscripts we are writing are the direction in which the field is pointing towards. So I should have an electric field pointing in x direction, but not only should it point in x direction, but it should also vary in y direction. Then hz component would exist. Also related to that, and not very clear unless we start, it'll become clearer when we do more examples, when we start doing the specific solutions, is that if a field component varies in its own direction, then that component of itself exists. If a field component varies in its own direction, if I have Ex, field pointing in x direction, and its amplitude is also varying in x, then my Ez term would exist. So now if we go back to the cases we had, we see that certain different solutions start to point to come out. Let's take the case of this red first. So if I have this parallel plate waveguide and I have a again we had said this direction was x, this direction was y. I have a field which is pointing in x, and because this field has to be zero and has to be zero here, this will have a variation in y. If this has a variation in y, that means there is an x component of the field which is varying in y, means Hz will exist. There is going to be a component of the magnetic field in the z direction. And we will, when we do the math, we will come up with this answer. So the solutions we are going to get for this case is going to be that there is going to be a field in Ex direction. There is going to be a component of the magnetic field in Y direction, and there is going to be a component of the magnetic field in Z direction. This is different than plane wave we had studied before, where you had a field in X direction and a field in Y direction, and the wave was traveling in Z direction. The wave here is still traveling in Z direction. The wave is propagating in Z direction, but now it has a small magnetic field which is rotating about Z direction too. Such a wave is called transverse electric wave. Basically, what it means is electric field E is transverse. Transverse basically is a fancy word for perpendicular. Basically, what this means is that for this wave, the electric field is transverse, but the magnetic field has a longitudinal component. This component is the longitudinal component or along the length, that's the propagation length, longitudinal component of X. Transverse electric is all the electric field is transverse to the direction of propagation, but the magnetic field has a component in the direction of propagation. This becomes one type of solution which can exist in this simple case of a parallel plane. What is the other solution which can exist? Let's take the second case we had. We had said we have somehow excited the electric field to be in y direction. Again, this is x, this is y. If this is varying in y, because this field does not need to be zero here, thus this field may not vary in y. This may only have a variation in z, may not have a variation in y. In that case, what you're going to get is an electric field pointing in y direction, a magnetic field pointing in x direction, and the wave is propagating in z direction. And this is your standard TEM wave. So you can have a solution where the electric field remains uniform inside this dielectric, inside this region. It just remains uniform over here, just like a plane wave, but it's just bound by the two conductors. And because the electric field is hitting the conductors at 90 degrees, it can exist. It is hitting it at normal. It can exist. So that can also happen. And this is going to be a TEM wave. And this is going to be another case of the solution. And the third solution is going to be, if I have the same case now, electric field pointing in y direction, but now also varies. The amplitude could possibly vary in y. I have I have two conductors, and in principle, the amplitude could vary in y. And if the amplitude varies in its own direction, then the z component of that field has to exist. So Ey will exist, Ez will exist, Hx will exist. So in this case now, you would have an electric field pointing in y direction, electric field, a magnetic field pointing in x direction, and an electric field pointing in the z direction, and the wave propagating in z direction. So you'll have these three different components of the two components of the electric field, one component of the magnetic field. And in this case, what you notice is the magnetic field component is always perpendicular to the direction of propagation, but the electric field component has a longitudinal component. So there is going to be, this is called a transverse magnetic wave, or a TM wave. This magnetic field is 90 degrees to direction of propagation, but electric field has a component in the longitudinal direction. So for this simple problem of bounding the wave into one direction, in y direction, we'll have three different solutions. We'll have a TE mode, the TE solution. We'll have a TM mode, transverse magnetic modes. We'll have TEM modes. Uh, what these solutions are, we'll start taking a look at from tomorrow onwards. Once you understand one of those, we'll start with the TE mode. Once we understand what the solution for TE mode looks like, TM mode comes out very, very quickly. It's just the same maths, but doing it in magnetic field instead of doing it in electric field. So we'll start looking at this maths tomorrow. I think it'll be a good place to stop here. Uh, I've laid the background of how we're going to try to solve this. So basically, tomorrow what we're going to do is we're going to go back to our Helmholtz wave equations. We're going to try to choose one of these two equations, which one works best for us. And again, we're going to try to find a solution, and we're going to tie that solution to the boundaries at the conductor. So obviously, the parallel boundary condition at the conductor works the best. E has to go to 0 there. So what we're going to do is we're going to say, all right, I know that the solution for TE wave is going to look like, I have an EX component, an HY component, and an HZ component. Maybe I can start with my EX component because that is parallel to the boundary, and it has to go to 0 values here. What would the solution be looking like inside? What happens to that solution? And we're going to find some very interesting results. We're going to see that only certain discrete solutions can happen. We cannot have any arbitrary distribution of electric field inside. Only very specific distributions of electric field can happen inside, and each of that distribution is going to travel with its own unique velocity. Is going to travel like a mode. Is going to travel like a mode of transport. Is going to have its own unique properties. We'll start looking at those solutions from tomorrow onwards. Uh,
Hello.
hello.
Dr. Simar, this is Dr. Sabinian.
Hi, Dr. Sabine. How are you doing?
How are you, sir?
Quite good.
Yeah, nice to see you once again.
Yeah, nice to see you too.
Yeah, first of all, I thank you on behalf of department for providing this kind of opportunity for our students.
Oh, no problem. It's a pleasure to be
Yeah, yeah.
speaking this year.
Thank
I
you.
always enjoy
I
it.
think I think daily you first 5 minutes. Can we have an interactive session with our students
Sure,
so they can go through their previous lecture
sure,
and daily morning you can have an interactive session. Then you can start the next day's session.
sure. Let's do that. Yeah. So basically, we can spend another 10 minutes tomorrow talking about today's lecture if they have any questions. What I'll try to do is I'll try to post it on YouTube. This lecture, I've been recording it, so I'll post it on YouTube if they want to take a relook at it.
Okay, sir. Thank you.
Okay. Anything else or?
You take, we will take the link from the YouTube, sir. If we have the link
Sure.
shared.
It will probably be sent to you by, I mean, it'll probably take me till the morning to upload it. So I'll send it to you by 8 or 9 in the morning, my time, 5, 6 your time.
Okay, sir. Thank you.
Right?
I'll share the link with the students so that the next day morning class they can ask any doubts.
Sure.
So
And
every day morning we will have a 5 to 10 minutes of interactions with each of the venues.
Sure.
5 minutes in each venue,
Okay.
and then
Good.
we will start our lecture.
Yeah, that'll be good. Yeah.
Thank you so much. Thank you.
All right.
We'll meet you tomorrow.
All right. We'll see.
Thank you.
All right. Thank you very much.